Hello, in this talk I will present a scheme to perform subtraction of massive black hole binary signals from laser data. Massive black hole binary merger events send loud gravitational wave signals. They are the loudest ones among all sources contributing to the laser band. These peaks here in the simulated data represent them. Moreover, MBHB signals are broadband in frequency, so they corrupt the power spectral density. We need to subtract them to uncover other sources. We came up with a fast scheme to detect and subtract them from laser data to the noise level. It includes a signal reconstruction method incorporating extrinsic parameters and a mesh-refinement algorithm determining masses and spins, which are intrinsic parameters. I'll first clarify the approximations we make with this scheme. We use an approximate IMR waveform based on long wavelength regime. We use a window of almost 2 weeks containing the signal to subtract. Laser constellation motion is neglected during the window. We only consider 2-2 mode as in data simulation. Now, let's look at the key tool called F-statistic. Taking an example of the A-channel TDI signal, it consists of some rescaling, transfer function, and the strain. We single out the antenna pattern function, Fa, which is constant in frequency due to our approximations, putting everything else into a function of frequency. In the end, A is the real part of Fa times h plus imaginary part of Fa times IH. Then, we maximize the log likelihood ratio, log La over the complex number Fa. The analytical maximum of it takes this form where n is normalization factor. The E-channel case follows analogically. In our scheme, we consider both channels, so F-statistic is the sum of log La and log Le. Let's have a closer look at these objects. Pattern functions depend on inclination, observer phase, polarization angle, and sky position. The rest depends on sky position, merger time, and luminosity distance from the source. So if we use F-statistic, at least we fully maximize over 3 extrinsic parameters, and we also maximize partially over sky position. But we can do better. Instead of the usual matched filter, we consider its time-shifted version. This induces a time-shifted F-statistic, which determines the time of coalescence through iteration, because sky position enters both pattern function and h. If we note this complex number Qa, where tau max is the time of coalescence determined above, we can reconstruct the A-channel signal as QAH in the frequency domain. Again, the E case follows analogically. Here we show the best results we can achieve using F-statistic. Assuming true value for masses and spins, that's why we said this was the best results. These results are very good in that the residues are at the noise level. Now, how to search for intrinsic parameters? Will the results also be good if we do that? We use a mesh-refinement algorithm called Vegas. It was first invented by Peter Lepage for elementary particle physics. It is essentially an algorithm of importance sampling when the function f is more or less separable. we try to approach F with a separable weight function g. The components of weight function g are computed iteratively. In each step, we sample F with respect to g. We take its maximum sampled with the final g obtained through iteration as the estimator. Evaluations of function can be easily parallelized, so we implemented this algorithm in a Python package. For illustration, here you can see the effects of this algorithm, where we only applied to chirp mass and mass ratio. Initially, the mesh grade was even. After 4 iterations, the grade became more dense where the function values are higher. Here is an example of the signal subtraction where masses and spins are determined with vegas. The reconstruction was done as introduced before. We see that the residue is indeed at the noise level for both A and A channels, and we have similar results for other MBHB signals. In summary, we find a peak above the noise level in the input signal, and we window the signal around that peak. We reconstruct the waveform with vegas and F-statistic. Then we subtract it from the signal, and we try to find the next peak. If there is no peak above the noise, then we are done, and we have the output. In conclusion, the scheme works very well. The residues are indeed at the noise level, and it is also fast enough. On a cluster, subtraction of one MBHB signal takes about 10 minutes if the search range is large, covering all possible parameter, which means it covers all possible parameter values. We can reduce it to about 2 minutes if we can narrow down this range. Besides, it has an additional benefit. The weight function we got with vegas provides a good initial guess for more precise parameter estimation in next step. Thank you for your attention.